Good morning, good afternoon, or good night. My name is Shirley, and my group and I are presenting our project on AI image detection using two neural networks, the feed-forward neural network and the convolutional neural network. Our presentation will start by going over a synopsis of the goal, dataset, general results, then moving on to our two neural networks and the analysis of their performance, and finally the conclusion. As we know from Professor Demeter, who always said, "I know this much, the field is this big," there are a lot of things that we are still figuring out in the machine learning world, and it is really important to keep track of how to responsibly and ethically use AI and machine learning tools. In order to do this, a key task is to first be able to identify between AI and human-generated data. The goal of our project is to distinguish between human-created and AI-generated images by running unlabeled images through our model and doing binary classification to predict a label. Now I'll pass it on to Minseo to talk about our dataset and accuracy results.
The CI fake dataset is a dataset of real and synthetic images generated with latent diffusion taken from Kaggle. It is a two-class dataset with real and fake as the two classes, which means that we will be utilizing binary classification within our machine learning models. There are 120,000 images total in the dataset, breaking down into 60,000 real images and 60,000 fake images. They are randomly divided into our training set, validation set, and test set, making sure that each set has an equal number of real and AI-generated images in it. For the training set, we have 80,000 images, equally divided between real and AI-generated images. For both the validation and test set, we have 20,000 images each, which are equally divided as well. The dimensions of each image are 32 by 32 pixels. Here are the F1 results that we achieved with our feed-forward and convolutional neural networks on the dataset. Our feed-forward neural network achieved an F1 score of 62%, and our convolutional neural network achieved an F1 score of 96.6%. The best score given by the convolutional neural network was 96.6%. The random sampling baseline was obtained by having the model guess either the real or fake label with 50% probability. As such, the F1 score and accuracy score is close to the 0.5 baseline expected when using a random sampling model for binary classification. The Matthew correlation coefficient is 0, which means that the classifier is no better than a coin flip. The confusion matrix also shows an equal distribution between each of the four quadrants. And now I'll pass it on to Coumba to talk about our first approach, feed-forward neural network.
First approach, we used the feed-forward neural network like we did for homework 3, and as we discussed in class, feed-forward is one of the simplest neural networks since it is unidirectional and the data flows in only one direction, and it is good for a task with single output like an image classification task. So for this specific model, we used 4 layers. We used ReLU and sigmoid as our activation functions, and we used the loss function BCE with logits. We also optimized our model with SGD. We had a learning rate of 0.01 and patience 1. We ran this over 10 epochs, and these are the results that we got. We got an accuracy of 0.57 and an F1 score of 0.62. And as you can see from the learning curve, our training loss is higher than our validation loss. And Elizabeth will discuss the results on the next slide.
For Matthew correlation coefficient MCC, we have a value of 0.1458, which is only slightly better than guessing, but this might be because our model is too simple for the task. 0 means it's no better than random, while 1 means there's a perfect agreement. Surprisingly, the validation dataset had consistently lower loss than the training dataset. This might be because the dropout was activated when training the data, but was deactivated when evaluating on the validation set. We were surprised that the stochastic gradient descent SGD optimizer had a better performance than the Atom optimizer. This might be because literature suggests that the SGD generalizes better than Atom. The inductive bias is the hierarchical composition of dense layers and the ReLUs that can universally approximate the target function f. The limitation is that the model is likely too simple to capture the underlying patterns. This led to the model predicting the same class.
For our second approach, we decided to try a more complicated neural network, the convolutional neural network, or the CNN as we'll refer to it from here on out. CNNs are particularly effective for image-based tasks, as they're designed for processing and analyzing structured grid-like data, like, say, pixels in an image. As such, CNNs are good for identifying spatial relationships and local patterns in images. The big difference from a feed-forward neural network was using convolutional layers to do the aforementioned feature detection, and then using pooling layers to reduce dimensionality while preserving important information. So, going over all of our settings and hyperparameters, just like in the feed-forward, we use batches of 100 for training and validation. We used ReLU for activation, binary cross-entropy with logits for the loss function, and the Atom W optimizer, which is essentially Atom but with better weight decay. Our CNN was constructed with free 2D convolutions, starting from free channels for the RGB to 64 filters to 128 then to 256. Then we ran it through free linear layers. We also introduced perturbations to the image data by randomly resizing and randomly flipping the images in the training and validation sets. Then, when training the model, we ran it on 10 epochs with a learning rate of 0.001 and stopping patience of 2. Now, Blake will explain the results of running our CNN model.
So here are our CNN results. As you can see, we achieved high scores on our F1, accuracy, and MCC metrics. Here, the F1 and accuracy metrics look like the same value, but they're actually slightly different at higher decimal places, as is expected. Looking at our learning curve, we see that apart from an unexpected spike in the validation loss at around epoch number 1, gradient descent has happened as expected, and the models seem to converge at a training loss of close to 0, although the validation loss is slightly higher. And for our confusion matrix, we can see that most of the examples were predicted correctly, either as true positives or true negatives. So the high MCC score of 0.932 indicates that both classes are predicted accurately. Usually MCC is used for unbalanced datasets because it's a better measure of the ability to predict the correct label when the dataset is highly unbalanced, and it performs better than the F1 and accuracy score. In this case, our dataset was balanced, but we just included it as an additional metric. So the high MCC score indicates that the convolution steps were likely able to extract meaningful features from the individual pixels. And also, the larger number of training parameters likely allowed for better fitting over the dataset. Now, the spike in validation loss that we see in epoch number 1, we're not entirely sure why that has occurred, but we posit that it's due to the random nature of training, where perhaps because of the way the model parameters were set up, we just saw a random spike early on in the training. And we see once again that training loss is lower than validation loss. This is likely also due to dropout since we added a dropout layer in our CNN. Moving on to some of the assumptions and limitations of our model. So the main inductive biases of a CNN, in addition to the inductive biases of a feed-forward, are firstly locality. So the idea that combining local pixels allows us to form features in a hierarchical fashion. And the second bias is translational equivariance, which is the idea that the model is able to learn even if the features are translated. And that's a property of CNNs that we tested by introducing perturbations to the data, such as flipping it or zooming in or zooming out on the data set. So one major limitation of the CNN model is that it is quite large. It has about 4.5 million parameters. So there is a rather high cost of training and inference in terms of the energy consumption as well as training time. Now, we'd like to conclude with some main takeaways. The first of which is that we found that convolutional neural networks generally perform better than feed-forward networks for image classification, and this is to be expected because the convolution steps are able to extract meaningful features from the pixel data. We also find that data pre-processing is integral, so we found that perturbations to the image, such as flipping horizontally or zooming in and out of the image, allows for better generalization. And lastly, empirically, we found that training is a noisy process that is highly dependent on hyperparameter settings. And what this has meant for us in our training is that slight changes to the hyperparameter settings can lead a model to either converge or not converge at all. Thank you.